Chapter 18 for AP Chemistry is looking at nuclear chemistry. We've looked at chemical reactions up to this point. Now we're going to be looking at what goes on inside the nucleus. When we're dealing with nuclear reactions, we're looking at the parts that make up the nucleus and how it changes. Chemical reactions involve interactions of electrons within the atoms. Those electrons move from one atom to another, but they don't change the nature of the element. In a chemical reaction, again, the elements' identities don't change. They combine and they rearrange in different organization. The identity of each element itself doesn't change. That's different when we're looking at nuclear reactions. The identity of an element changes when we have a nuclear reaction. We have changes going on in the nucleus in the form of radioactive decay. We have two kinds of isotope. In a nuclear reaction, the number of protons or the number of neutrons change, and what we get then is a new element. Stable nuclei don't go through radioactive decay, so isotopes of elements that are stable don't change. They maintain their identity in any kind of reaction. They do not have nuclear changes. Unstable nuclei do go through nuclear changes, and they go through radioactive decay. The attempt of these isotopes is to become more stable. There's several ways that a nucleus can become more stable, several ways it can decay. What we're going to look at first is this chart, this graph on the right, that relates the number of neutrons in an isotope to the number of protons in the isotope. And what we see is for the first 20 elements, the ratio of neutrons to protons is roughly 1 to 1. So if you look at the atomic mass, it's roughly double the atomic number of the isotope. Atomic mass, again, is the number of protons plus the number of neutrons in an atom. The atomic number is the number of protons in that atom. As we look at this chart, what we see is that 1 to 1 ratio continues up to about element number 20, and then it gets a little bit different. What we see is a series of dotted lines or dots creating a line called the band of stability. Each of those dots represents an isotope, and for a particular atomic number, there may be several isotopes of that element, and those are represented as dots vertical relative to each other. If the dots are right along the band, then those isotopes are stable. If they are above the band or below the band, then we have some unstable isotopes, and those are the ones that are going to decay. In general, when we're looking at nuclei, what we're going to find is as the atomic number increases for elements, what we see is we need more neutrons to help maintain stability. So 1 to 1 ratio up through element number 20. As we get above element 20, we need more and more, and eventually it gets up to about a 1.5 neutrons to 1 proton ratio to maintain stability. Another thing that researchers have found is when they compare atomic nuclei, what they find is that elements that have an even number of protons and or an even number of neutrons, then these isotopes tend to be more stable than those that have an odd number of neutrons and or a number of protons. Nuclear reactions or nuclear decay is what an isotope will go through if it's unstable so that it can attempt to become more stable. We're going to take a look at 3 types of natural radioactive decay, and each of them depends on where the isotope is relative to that band of stability as to the type of decay that goes on. We have isotopes that some of them are above the band of stability. We have some isotopes that are below the band of stability. We have another group of isotopes that are beyond the band of stability or the zone of stability, and each of those different types of isotopes goes through a different type of radioactive decay. We're going to start with elements that are above the band of stability. In this case, we have too many neutrons. So the isotope wants to go through a process to decrease the number of neutrons, increase the number of protons. So what happens is the neutron actually breaks down. Beta decay generates beta particles. Beta particles are electrons generated from the nucleus. Same mass, same charge as electrons outside of the nucleus, but they come from the nucleus, and they come from the neutron breaking down. When we write nuclear reactions, we write the symbol of our particle. We also identify its mass and its charge. The mass number is the top number, the charge number is the bottom number. Neutrons have a mass of 1 atomic mass unit, and they have a charge of 0. They're neutral particles. So when a neutron breaks down, we're going to get this beta particle. Electrons are 1,000 times less massive than neutrons, so their mass is effectively 0. but beta particles, electrons, have a charge of -1. When we're doing these, just like in chemical reactions, we need to make sure that we conserve matter. So our top mass numbers need to add up. On the left we have 1. On the right we need to have 1 as well. So we need a particle with a mass of 1. On the bottom we have a charge of 0 on the left. So on the right we need a particle that has a charge that when added to -1 gives me 0. What we get then is a neutron decaying to form a beta particle and a proton. So by changing from a neutron to a proton, we change our atomic number, we change the identity of the element. So neutron beta decay gives us a proton and a beta particle. An isotope that goes through beta decay is carbon-14. Carbon-14 is most commonly associated with radioactive biological decay. It's the only radioactive isotope of carbon. When carbon-14 decays, we get a beta particle and we get a new element. We get stable nitrogen-14. Anytime we have a nuclear decay, radioactive decay, we also get gamma radiation, pure energy. The next type of radioactive decay we're going to take a look at are elements that are below the band of stability. These elements don't have enough neutrons. There are actually two ways that an element can try and become more stable. One way is positron emission. A positron is same mass as an electron but has a positive charge. It comes from the nucleus and it is a result of a proton breaking down and a neutron being formed. So positron emission decreases the atomic number of an isotope without changing its mass. So a proton with a mass of 1, a charge of 1, generates a neutron with a mass of 1 but a 0 charge. And then we got this little tiny particle that has a mass of 0 and a charge of +1. We also get gamma radiation. The way we tell positrons from electrons is electrons have the -1 charge, positrons have the +1 charge, and that's really about the only way we can tell them apart. An example of an element isotope that goes through positron emission would be phosphorus-30. So phosphorus-30 will kick out a positron and then it will form an isotope that has the same mass, so silicon-30, and it has 1 fewer protons because one of the protons has broken down. The other way that we can increase the stability of these isotopes that have too few neutrons that are below the band of stability is to go through a process called electron capture. This is where the nucleus actually snags one of the electrons in the lowest energy level from outside the nucleus, pulls it in, and that electron combines with the proton to form a neutron. So in this case we have two particles on our reactant side. We have a proton and an electron. They combine to give us a neutron. Same mass, neutral charge. Again, we have gamma radiation as we do with any kind of radioactive decay. An example of an isotope that goes through electron capture, could also go through positron emission, would be argon-37. So argon-37 captures an electron, so we're going to get an element that has 1 fewer protons. That would be chlorine, same mass, so chlorine-37, plus some gamma radiation is generated.